Hello, everyone. I will present our work on decision rule elicitation for domain adaptation. The work was done jointly by me and Samuel Kaski. Our work provides a way to make a more effective interaction between a machine learning model and a domain expert. I want to start with an example. Assume we want to solve a predictive maintenance task, which means to provide a piece of information about future breaks to a maintenance engineer. A set of workstations is presented in the left upper corner. Some of these workstations are broken and we need to predict the state of a particular workstation marked with a question mark. We map all the workstations to a high-dimensional feature space. An artificial intelligence system makes a prediction and asks a human to check it. The domain expert returns an explanation of their heuristical decision-making to the system. Essentially, our work proposes to use these feedback rules for improving machine learning predictive performance and, in particular, domain adaptation quality. Our approach is based on empirical observations and psychological studies. We have noticed that domain experts can explain their decision-making via simple heuristic rules. A general decision rule that describes a solution to the whole problem might be quite complex compared to a case-specific rule of thumb. We found that heuristical decision-making was confirmed in psychological literature by fast and fragile trees. These trees describe heuristics that specialists use for decision-making. For example, the nurse's heuristic in the right picture. Compositions over decision trees are a powerful tool in machine learning, and we will utilize decision rule feedback in a similar fashion. Our algorithm can be written as follows. We use a standard notation for feature and target spaces. SIGCHI is a machine learning model that is trained on historical data. Fi are the feedback rules that experts provided for a data point XI test. C feedback is a composition algorithm based on the feedback rules. It is a weighted sum of all the rules with weights θi. The weights θi can be set from prior knowledge or learned as the algorithm's parameters. Sim is a similarity function between the data point X and data point where the feedback rules were provided. Lastly, sigma is a smoothing function. The result model is an average of the machine learning and feedback-based models. It is a weighted average with coefficient alpha, and alpha can be a function of X. In the experimental parts, we did both user modeling and user studies. First, we considered the dataset pictured on the right-hand side. We modeled each user with shallow decision trees, parameterized them with a depth of decision trees and human experience, which means a fraction of seen data from both train and test domains. We modeled 40 experts and observed that decision rule feedback improves both training and test domain performance. We compared it with no feedback at all or correct labels as feedback. We conducted a user study on the same setting as the previous one, but using real experts. We observed that our approach improved the performance here as well. Next, we evaluated the method on a more challenging task, sentiment analysis. We considered a model trained on the IMDb dataset to predict the text's sentiment. We evaluated it on the Amazon review dataset that contains 25 different topics. Thus, it is a great case to test domain adaptation properties. We conducted a user study with the same set of people as in the previous case. Participants have been asked to provide generalizable rules based on the examples misclassified by a machine learning model. Here we will show illustrative results for 4 topics. We can see that often logistic regression combined with decision rule feedback outperforms logistic regression with labels as feedback. These are orange lines compared to the red lines. Of course, it outperforms the model trained on IMDb for some alpha values for all the cases. It is green line compared to the orange line. And we provide the results for the rest of the 25 topics in the paper as well. The main take-home message is, if the domain experts in your problem can explain their decision-making explicitly, our methods likely will improve the performance and help with domain adaptation. As a future extension, it is crucial to bridge the gap between our predicate-based feedback mechanism and natural language. Thank you for your attention.